This is also called conjugate addition when we attack at the 1,4 position. We talked last time about how when there's alternating single and double bonds, we call that a conjugated molecule. So here we have something conjugated with alternating single and double bonds. So attack at the 1,4 position is also called conjugate addition. Attack at 1,4 here is called conjugate addition. All right, so how can we decide if we're going to do the 1,4 or the 1,2? Well, first of all, as a rule of thumb, if you have to take a guess, you should guess that it's going to be 1,4 addition. Most nucleophiles attack at the beta carbon in this situation. Most nucleophiles attack at the beta carbon. So if you have to take a guess, you should guess 1,4, attacking at the beta carbon. And then you should just memorize the exceptional nucleophiles that would attack here. So let's see, one nucleophile that would attack here is alkyl lithiums. Remember, those are a type of organometallic reagent. So organolithiums, alkyl lithiums, I'll put them over here to indicate these would do a 1,2 addition. They would attack the carbonyl carbon. By the way, have you guys been, you guys have probably covered, now at this point, it's usually typical to cover organocuprates again at this point.
Those attack at the bottom of the beta carbon.
These would attack at the beta carbon. These would be a 1,4 addition. I always forget how to write these.
CULI.
Thank you. And remember that it's just a technicality that there's two R groups. Only one of them is going to attack the beta carbon. So these would attack in 1,4 addition. I think sometimes these are also called Gilman reagents, but I don't know if the book uses that term.
Yeah.
All right, Gilman reagents or organocuprates. So organolithiums do attack at the carbonyl carbon. Gilman reagents, organocuprates, attack at the beta carbon. It would be natural to ask, what about Grignard reagents? But I don't think your course is going to test you on Grignard reagents because those are complicated. Grignard reagents might attack at either carbon, or there might be a mixture depending on the conditions. So you're probably not going to see any problems about Grignard reagents, and you probably shouldn't use those on syntheses for this type of situation. So we won't need to worry about how Grignards react here, just the organocuprates and the alkyl lithiums. Let's see, I can only think of one other type of molecule that's likely to attack at the carbonyl carbon here. Now, if you just have a normal amine, that will probably attack over here. If you just have a normal amine that looks like this, you'll probably get a 1,4 addition, mainly. But remember that we've seen a bunch of types of amine derivatives, where instead of having a carbon chain attached to the nitrogen, you have some other functional groups. For example, you might have another NH2 group like hydrazine, or you might have a hydroxy group, which I think is called hydroxylamine, or there's even, I don't know if you guys worry about this, but there's even this big complicated thing that I think is called a semicarbazide. Anyway, instead of having a carbon chain attached to the nitrogen, you could have a bunch of nitrogens or oxygens attached. I guess we'd call these amine derivatives. Well, a normal amine with a carbon chain, we just said does 1,4 addition. But these amine derivatives, I put them under here to show that these do 1,2 addition. So all of these types of amine derivatives, where instead of a carbon chain, we have a nitrogen or an oxygen attached, those would attack the carbonyl carbon. That's pretty much all the ones that I think you need to know that would normally do 1,2 addition. Just alkyl lithiums and these amine derivatives. Pretty much anything else you can expect to attack the beta carbon.
Grignards.
He said Grignards because they're too complicated and they would attack both.
They're in our, I mean, we talked about it in our,
For 1,4 addition or for other things?
for both, for 1,4, he said like to know for both.
Okay, what the textbook says about Grignards is that they're complicated and it doesn't talk about it. But if he gave you more information in your lecture notes, then you'd have to know that. So you'd have to look that up in your lecture notes if he gave you specific information about Grignards. Oftentimes, Grignards are left out here because they are kind of complicated. But if he gave you some specific details he wants you to know, then maybe you
But
can
they're
take
left
that.
out in the textbook?
The textbook just says what I just told you. The textbook says sometimes a Grignard attacks the carbonyl, sometimes it attacks the beta carbon, sometimes it attacks both. It depends on the exact reagents.
Yeah.
So if he gave you more information in lecture,
Yeah,
then
I
you'll have
saw
that.
but-
Okay. All right, so we should just look at a couple of examples of these types of attack. Does it make sense so far?
Mhm.
Yep.
Okay. Okay, well, let's do the mechanism for this reaction. Looks like you turned this into an enol, but it turns out that's actually not the key reaction that we want to have happen here. So basically, the key thing we want to see here is that we've got a nucleophile, and we simply want to have the nucleophile attack one of the electrophilic atoms. This does not really involve the idea of an enol or tautomerization. This isn't really a
I
tautomer.
thought just through resonance it becomes like that.
Ah, I see. You just do a different resonance structure. Okay, that's right. So let me take another look at what you drew.
So that it can attack this.
Ah, gotcha. Now, first of all, notice that this is not a resonance structure of this because you've moved the hydrogen. If it was a resonance structure, all the,
hydrogen is still there.
how about the hydrogen on the oxygen?
That's from the H3O plus.
But that's the second step. That shouldn't happen until this guy attacks. Oh, have you already done this? Oh, I see what's happened. I see. Okay. Now I see what's going on. So what you did is you did this.
Yeah.
All right. However, remember that an alpha beta unsaturated aldehyde has two different electrophilic atoms, the beta carbon and the carbonyl carbon. Which one does an alkyl lithium attack?
The exception, which is the
Uh,
carbonyl.
Yeah, it attacks the carbonyl carbon. All right, so it took me a while to see what you were thinking there. Okay. We said that most nucleophiles will attack the beta carbon, but not alkyl lithiums. Alkyl lithiums are an exceptional case. They're going to attack the carbonyl carbon, which means that this should be a reaction that's very similar to the reaction that we've done in a bunch of previous sessions. This is just a normal nucleophilic attack on a carbonyl. So we should ask, is this category 1, 2, or 3?
Category, yeah, 1.
Category 1. We've seen that organometallics attack an aldehyde or a ketone just once. Okay, good. I think you might not have the right numbers of carbons here. Did you? It's a good idea to number this. Good, and then number the subsequent picture. Anytime we're making, adding or dropping carbons, it's very easy to make mistakes if we don't add a few numbers. I don't have to number this carbon because I'm asterisking it. It's still a good idea here to asterisk the carbonyl that's acting like the electrophile, but I'm going to number these carbons so I don't lose track of them. There we go. Good. And now at this point, it's a matter of taste whether we keep showing this hydrogen anymore, because now we could just treat this like a normal hidden hydrogen, so you can leave it in or take it out, whichever you like. The crucial thing is to get the correct connectivity for the carbons, and that's where numbering always becomes very helpful.